Hey, so we've been talking about systems of equations for about a week and doing a lot of work with the various types of linear equations. And you may notice that most of these are the things that you've been working on, graphing and matrices, linear combinations, and substitutions. The tables in the setting equal stuff from Math 1 that you probably have, hopefully are still familiar with. The question is, how do we decide which method to use? Which method's going to be the best method for us to work out, when we decide to use each particular one. So the answer is it depends. Depends on what our goal is, what we're trying to do. What do we need to find out? Are we looking for an approximate answer? Are we looking for an exact answer? That's, that would be sort of the first piece that we might want to know about. How are the equations set up? Are they set up easily so that we could graph them? Are they set up easily so that we could do substitution? Are they set up easily so we could do linear combinations? Typically, we want to go with what's kind of the easiest method for us to work with. Do we have technology available? Do we have graphing calculators? Can we just graph the lines and make it all work out? Can we use matrices? If you don't have a calculator, doing the matrix inverse is a whole lot more work than with the calculator. And the bottom line is, which one are you most comfortable with? So if you're most comfortable, I'll get it this time, if you're most comfortable with substitution, then it might be worth the time for you to rearrange the equations so that you can use substitution. If you're most comfortable with linear combinations, it might be worthwhile to rearrange so that you can do linear combinations. If you love doing matrices, then, it's probably worth the time to do the matrix setup and make it work out that way. We want you, of course, to be able to do all of these things, and that's what's going to be on the test. So we just want to do a quick review of when and why and which ones are going to be the best things for us to deal with. So graphing, there's a couple of different graphing options that we have. So it's blue pen. Let's say we want to graph something like y equals 3x plus 5 and y equals half x plus 10. And if we're graphing, as we said, you get an approximate solution. If it turns out that the answer is right on one of the crosshairs, like right there, then we can pretty much tell what it is. But if it's kind of here-ish, then we've got to guess a little bit. But ultimately, with graphing, we want a general idea. Do we have a solution? Do we not have a solution? That sort of thing. So if we look at 3x plus 5, we're going to start at 5. 1, 2, 3, 4, 5. And our slope is 3, so we go up 3 and over 1. Okay? See if I can make a line. That goes roughly through those points. Not bad, I guess. Move it around a little. Look back. That's all it's good. All right, and then half x plus 10. And start at 10. Start at 10. 1, 2, 3, 4, 5, 6. No, wait. 1, 2, 3, 4, 5. There we go. 6, 7, 8, 9, 10. Okay. Now if we do a half, well, it's going to be way over there. So, well, let's see what happens here. If I do a half, I'm going to go up 1 and over 2. So I guess I'm going to have to go down 1 and back 2. That makes some sense. That might work, and God, it's going to be awful because we can graph these, but we're not really going to be able to tell exactly where they cross because they're crossing off my graph. That'd be a problem, right? So maybe what I should have done was use these as counting as 2, and then it would show up in the end here. But ultimately, we would get some sort of an intersection. At the very least, we'd know they intersect, okay? If we graph them and we get a couple of parallel lines, we know that means no solution. And if we end up getting, like the same line just right on top of each other, that's the case where we call it many solutions, okay? So if it's in this form and you want to graph it and you love doing the slope-intercept graphing, go for it. If it's in this form, 3x plus 4y equals 12, and 2x minus 6y equals 12. Those are my standard form equations. Many of you like to solve these for y and then go back to this method. It's fine. If you like, we can do it with the cover-up method. That is, I think, a little faster. I'm not even bother with that. It's not going to give me enough information. If I pretend this isn't here, 3 times what equals 12? So what is 4? So my x-intercept is 1, 2, 3, 4. Y-intercept by the same thing is 3. I'm going to, that's awful. Let's not do that. I'm going to actually get the line tool and draw a beautiful straight line like about that. Much better. And for this one, what did we say? This was 4. That was 3. For this one, my x-intercept is 6. way out there. My y-intercept is going to be -2 out here-ish. Grab that. Draw me a line. Okay, rough in where they cross, and they don't seem to cross in a nice, lovely place, but my outlines are a little off anyway, so I might solve this 1, 2, 3, 4, 5, -1, something like that. 5, -1 might be where they cross. Remember, x, y, like in the alphabet. Okay, there's x, there's y. Okay, so there's one way. Matrix equations. If we have matrix equations to deal with, make sure my calculator's on. Hang on. And we're back. There's brief interruptions of setting up the calculator, so that's all ready to roll. With matrices, as we remember, we've got to have technology in order to use the matrix equation. So for a matrix equation, we'd have, 5x plus 3y equals 7, 2x minus 6y equals 18. We remember that these need to be in standard form for the matrix equation to work. So we work it out that way. If we pop in 5, 3, 2, -6, x, y equals 7, 18. So that's pretty systematic. The big thing, we've got to make sure we keep track of our signs. Got to make sure that things are in the right place. Don't get tricked by a different order. Don't get tricked by standard form. Go to the calculator, which I just do like this. Go to the calculator. I've got these matrices stored in. That's what I did during the little break. I go to matrix. I've got a 2x2 with my numbers in there. Matrix A, inverse, times, matrix, times, what does it do? Oh my goodness, wait. Try this. Second matrix, C, exponent, that's not going to work, is it? I would think not. Alright, so what are we doing here? Let's clear this out of here. We'll try it again. Alright, second matrix, A, inverse, times, matrix, C, bingo, there's my answer. It's nice because decimal numbers 2.66 and -2.11, which are not ones that we would necessarily come up with on our own. So we would then go, x, y equals, and I don't remember what the numbers were, but I think they were this, 2.11, matrix, answer, done, quick, pretty convenient to work with. Table. So if we had a couple of equations that we wanted to use tables, this is a Math 1 skill from way back when. Say we want to know when's y equals 4x minus 7 equal to y equals 3x minus 3. We could just go to our graphic calculator. We can go to y equals, pop those two equations in there, and basically look for where the tables intersect. So second table. Okay, what we're doing is we're looking down these y values until we get the same numbers. No. Oops, there it is. Okay, so my y values are the same, so my x values are the same at that place as well. So 4, 9, there's my solution. Okay, 4, 9. All right, so that's the easy way to do. Use the calculator. If you've got a calculator, technology, they're in standard or in the slope-intercept form. Life is good. Setting equal, same sort of thing. This is another one from Math 1 that we saw a couple problems like y equals 8x minus 8. Set them equal. Say 5x plus 7 is equal to 8x minus 8. So this y is equal to that y. So we make them that's y and that's y. And then our just strategy is just to get the letters on one side, the numbers on the other. Subtract 5x. Subtract 5x. For some reason you guys love the bar, so we'll put it in there. 7 equals 3x minus 8. Add 8 to both sides. 3x is 15. Lo and behold, x equals 5. What's y? Y is 5 times 5 plus 7. 5 times 5 is 25 plus 7 is 32. Okay? If we tried to graph that one, wouldn't really be really nice because, we'd have to have a really giant graph that goes way up here or up here, something like that. So, setting equal. We've done that before. Should be familiar with that. Linear combinations. Linear combinations. That's what we've been working on. That seems to be the one that's most difficult for folks as we work through these problems. A couple equations like this. So the goal is to make these numbers, the y's, I always go for the y's, you can do the x's if you like, make the y's have the same value but opposite sides. So real quick, stop this one by 4, that would make this 4, and go. I always like to have you write the equation when you've done the multiplication right next to the ones you have. 4 times 30 is 120, 128 or something like that. Okay? Add them together. These are going to undo each other, kill each other off, whatever you want to say. 27x equals, what does that turn out to be? Something. 151, maybe? Why it's 151, but it is. And then we just divide by 27, and we get some number like maybe, what would that be? Would it be 5? Would it be 5? No, probably wouldn't be 5. I guess I would jump to my calculator with 151 divided by 27. Hopefully it's a nice number that I'm just not seeing. 5.59. Excellent problem, Mr. Pig. 5.59. X equals 5.59. And then we just run back and we solve. The thing with these, you can do these easily. The way to tell we have no solution is to talk about, well, if we get something like 3 equals 0 or 0 equals 3, that means no solution. So if everything wipes it out except for the numbers, if we end up with 0 equals 0, that's the case where we have many solutions. So because 0 is always equal to 0. Okay? Substitution, that's the one everybody loves. 5x plus 3y equals 71. Oh no, my time is up. 6x minus 7. Let me stop Bob. Let me see what really I have for time. Oh, I've got 3 minutes. Look at that. I'm talking faster than time even could imagine. So, 5x plus 3 times 6x minus 7 equals 71. Okay? You guys are experts at doing these, so no need to go through in great detail. 5x plus 18x minus 21 equals 71. 23x minus 21 equals 71. 23x is going to be 92. And this time, it works out that x is 4. Yay, for picking a good problem. Easiest way to get this second answer is just go back to this one that says y equals. Some of you like that one, but that's more work than you need to do. Y equals 6 times 4 minus 7. That's just arithmetic. 24 minus 7, 17. Okay? Same thing with these. If you get like, when they're all done, you get like 0 equals 7. That means no solution, because 0 is never equal to 7, is it? And if we get 0 equals 0, that means we have many solutions. Okay? And just the other one that we didn't mention, back to matrices. When we get that singular matrix error, that means no solution. Right? Remember that? So we want to be able to recognize when we can't solve the equation. When, if we graph the lines, they'd be parallel, that sort of thing. They all mean the same thing. We'll just get the information in a different way. Lots of information for you. All just really quickly gone through. We went through 7 different versions in about 14 minutes. But they're all things you've seen. We just want to make sure you have it all in a nice summary form so you have some good notes when we take that test in a couple of days. Okay? Oh, word problem. That's what we're going to do next. Give you some help with that in a little while. Thanks for watching. We'll talk to you soon.